Okay. So today's lesson, I've kind of alluded to this. We don't have a lot less left to learn in this particular chapter before we get into kind of the meat of what Calc 2 really is if you guys end up doing it or redoing it in college. We have polar functions today. We actually have 2 different days of polar functions, today and next time. Today, in my opinion, is the much easier of the 2 days. It's gross looking. Like, I'm going to show you guys. So don't get intimidated or scared off by this because it's not hard. It's just a lot of trig within a problem. So, and again, I put that up here not to like scare anyone off because the problem, in my opinion, the problems today are pretty easy. There's a lot, so like you need to be very careful, but they're not hard problems if you know the unit circle. That's what you're going to be using today. If you know how to find the derivative of sine and cosine, and you know how to use the unit circle, today is not bad at all. The problems can take some time, as you can see, but I'll give you some tips and stuff of what I think might happen on the actual AP test, okay? Next class, I think next class is tough because what happens next class is we get into integrate. Today is all about derivatives. And then next class is all about integrals, like finding the area inside of these polar functions. I think the hardest thing is finding the limits of integration for next class, okay? So the reason I'm talking about next class, the reason I published the next Canvas page, so I was struggling with how to find the limits of integration. I was struggling with it. And so I looked on YouTube and I found a couple really good videos. There's 2 of them. And they're about 30 minutes each. And I'm not saying you have to watch them. But I would encourage you guys before next time to watch a little bit, at least the setup of the problems. They're 30 minutes because he will set up the integral, but then actually do all the integration. And I wouldn't watch that stuff. That stuff you guys will be fine with. It's just setting up the integrals and finding the limits of integration that if it were me, I would watch some of that before next class. So when you come in, you already have an idea and you're not lost when I'm teaching. That's just my advice. And that's why I published the page. Okay. And when I saw those videos, it helped me. Like I can do the problems quite easily now. It's still hard for me to teach them and explain how to find the limits. But if I'm given a problem, like I can do it. But like I said, it's tough for me to kind of explain how. So I think those videos might help. So that's why I published that page. So today, let's open up the notes about polar functions. And kind of like with parametrics, I do briefly just want to remind you guys what a polar function is in case you didn't watch the video from a few lessons ago. And that way we at least have some background knowledge, okay? First and foremost, you guys are not going to have to graph polar functions by hand, okay? When you are given, if you are given a polar function on the AP test, they're either going to show you the graph, which that's what they have started to do most often. Like on an FRQ, they just show the graph. Or it'll be calculator active and you'll be able to graph it in the calculator, okay? So with parametrics, I showed you guys how to change the mode and do parametrics. You're probably never going to do parametric mode in your calculator on the AP test, okay? I wouldn't do it. Polars, you might though. So I'll kind of show you kind of what it looks like. So to remind you guys how you graph or plot a polar function. So first of all the ordered pairs are in r comma theta format. And I don't know why they are this way. And I'll explain why I don't know why they are this way. But the R stands for the radius. If you look at this graph here, this is a polar graph. And each little ring represents a radius of 1 more unit. So like the inner ring right here is a circle with radius 1. The next one is a radius of 2, and then 3 and 4. So each circle represents 1 more radius, okay? The theta is you kind of going around the unit circle to find where to plot your points. So I don't, because you rotate first and then do the radius, I'm not sure why they have it in this format. I'm really not sure. But if I wanted to plot the point 3 comma pi over 3, the first thing I do is I rotate to where pi over 3 is. So you're starting on the x-axis, you rotate to pi over 3. Notice that there are 5 things here. The 3 that we are interested in, the 3 that you guys are most familiar with are the pi over 6, the pi over 4, and the pi over 3. The first two, I'm not exactly sure what those are. We could figure those out, but I'm not going to worry about those. So pi over 3 is going to be, so pi over 6, pi over 4, pi over 3. And then we're putting our point along this line on the circle that has a radius of 3. So 1, 2, 3. This right here is the point 3 comma pi over 3. That's how polar graphs work. You rotate and then you go out a certain distance. And I think in pre-cal you talk about how to convert from polar to Cartesian. I know in regular they spend a good amount of time on it. And we use that knowledge in this class. Next one is 0 comma pi over 2. So we're going to rotate to pi over 2 all the way at the top. The radius of 0, well, that's just at the origin. So anytime your radius is 0, the angle doesn't matter. You're at the origin. 5 pi over 4, 2 comma 5 pi over 4. So the way I count around the unit circle, I don't know how you guys do it. You just have to have a way. But if I'm doing by 4s, I go like this. I go 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and then 5 pi over 4. That's how I count with my 4s. Same with 6s. And then I'm at 2. So I'm here. That's 1. That's 2 right here. Again, you're not going to have to do this on the AP test. I'm just reminding you how polars work, how you rotate, and where the points come from. Last one, negative pi over 6. So that's going backwards, pi over 6. So here, radius of 4. 1, 2, 3, 4. Okay, so that's your background knowledge on polar functions. All right, now we kind of move into the calculus. Imagine that they're dealing with a calculator active question and they don't give you a graph, but they give you the function. So I want us to graph this in our calculator. I want us to graph r equals 3 cosine of 3 theta. Usually they'll provide the graph for you. It's not a guarantee, so you might want to know how to do this in your calculator. So again, like with parametrics, I would change my mode, but this time I'm going to change it to polar mode. So it says function, parametric, polar. So change it to polar. Then go to y equals, and now your functions are r equals. And I entered 3 cosine 3 theta. I did this already while my Algebra 2 class was quizzing. And then you push graph. I already kind of changed my window a little bit, but there is a polar function right there. That is 3 cosine 3 theta. You, again, will not have to know how to graph that by hand. I wouldn't, to be honest. So other polar functions that you guys might come across, I'm going to show you some of these graphs. I knew nothing about polars when I started teaching this class. I never learned it in any class I ever took, high school and college. So to me, when I first learned this, it was new. Here are just some other graphs you guys might come across, just so you understand. They're not all just going to be like leaf petals like this. You might have little loops inside of loops and things like that. But again, they're either going to give you the function or you're going to be able to graph it by hand. What's going to happen to kind of allude to next class? Did you find it?
They're having some.
Are you in radian mode?
Yeah. I think you need to go to window and change the theta step, and that should make it work.
Change theta step?
Yeah, and change it to a lower number.
Oh, wait. So I also wrote on here, change the format to polar GC. I don't know what that means. What was I going with there? Change format to polar.
Yeah.
Where's format? Second zoom. Ah, okay. So if at home you were struggling with that, oh, see, I like how I typed my notes to myself. If you go second zoom, I wonder why mine did it even though I was on rectangular. Why would that be? I don't know what I'm doing. Like, I don't know why mine's not on polar, but it's still graphed correctly. Did that work?
No, not that. I mean, zoom standard.
But changing it to polar, did that?
No, because I think about it.
It did. It just looks like it.
Yeah, but I just wish it was the same.
Oh, I don't know. I don't know at this moment in time. I don't know why I wrote change it to polar, but I don't have mine on polar and it works. Anyway, if yours graphed correctly, then just do you. Okay. So again, next class, what's going to happen? You're going to have to find limits of integration of these things. They're going to say like, find the area of this whole figure. Now, the nice thing with polars is they're always symmetrical. We're going to use a lot of symmetry next class, where when you find your area, like you'll find the area of one of these little leaf petals and then just multiply it by 5. But we're going to have to find the limits of integration to find the area of this one leaf petal. And that's what those videos are about. And that's what I'll kind of teach next time. So anyway, let's jump into today. So they're going to ask you, kind of like with parametrics, to find slopes of tangent lines. That's going to be a big thing that they ask. And so we're going to be dealing with dy dx. Okay. And the other thing they're going to ask you about is area. And that's next time. So today is all about derivative. Now, here are the things that you guys need to remember going back to pre-cal. These are kind of your 4 polar formulas that you guys have to be able to do and go back and forth. Like you're going to have to go from polar form to rectangular form, and then from rectangular form to polar form. So these first 2 take you from polar form to rectangular form. That's how you find x and y using your like what they tell you in terms of polars. If you know the rectangular info, like what x and y are, and you want to find the r and the theta, that's what the second 2 do. These formulas find you your polar info. And you guys did these in pre-cal. Is that fair? I know it was right at the end, I think, right when you guys went to quarantine. Am I right about that? You guys took a test at home, I think. Did you guys do a test at home over these?
We did a test at home over something.
You don't remember? It was right when quarantine started. I thought my AB class, I was talking to them about polars, and I thought they had said, but maybe not. I don't know. Anyway, okay. So we are going to learn a derivative formula, but the nice thing is it's not a formula you're going to have to memorize, but you have to know how to find it. Okay. So if I know r and theta and I want to find dy dx, if they ask me to find the slope of a tangent line, I need to find dy dx. And the way we find dy dx, it's going to be dy d theta over dx d theta. Very similar to what the parametric was, dy dt over dx dt, just now it's dy d theta over dx d theta. So we need to find these 2 things. We have to find dy d theta, we have to find dx d theta. Okay, so here's the thing. Y is r sine theta from above. X is r cosine theta from above. R is always going to be given to you as a function of theta. Like the problem is going to say, let r equal, like in this one, 3 cosine 3 theta. Like they're going to define r for you as some function, okay? So the way we're going to find this, if I want to find dy d theta, and r is a function of theta, that means we have to do product rule. To find the derivative of y, r is some function in terms of theta, and then times sine of theta, we have to do product rule to find dy d theta. So it would be first times derivative of the second, so cosine, plus second, so sine, times the derivative of the first. So here's how I'm going to write that. So that is dy d theta. It's going to be our job to plug in whatever r is for r and r prime. Like they'll give you r, and you'll plug in that function for r. You'll plug in its derivative for r prime. We'll practice that on the next page. Dx d theta, we do the same thing. To find dx d theta, we're going to do product rule with r cosine theta. So first times derivative of the second. The derivative of cosine is negative sine. So I'm going to write that as negative r sine theta. And then plus r prime cosine theta. Again, this is just me developing the dy dx formula. That means that dy dx is always going to be, now if you're someone who you have like a really good memory and you just want to remember this derivative formula, then you don't have to go through all this stuff. You can just remember the formula, but we're putting, this is how you'll most likely see it. So I'm going to flip the terms. I'm just putting the second term first. The reason they write it this way is mainly for the dx d theta to put the minus in between. It really doesn't matter how you guys write it. But this is our derivative formula for polar functions. If you're someone who you don't like to memorize things, and if it does show up, you need a way to get to the answer, then this is what you're going to be doing if it does show up. The nice thing is polars are rough, and I mentioned how it could be a full FRQ, but they won't make or break you. I've learned that. Like, you want to know enough to get you some points, but if you don't, I don't know. The first year I taught this, I was like, man, this sucks, and they're not going to know it, and they're all going to do bad. They were fine with it. They knew enough, and most of them got 5s. But all right, so we're going to practice. So you can either memorize this formula or know how to get to the formula. Either way, choice is yours. Choice is yours and yours alone. All right, so first example. Find the slope of the tangent line to the polar curve r equals 1 plus 2 sine theta at theta equals 0. So this is us finding dy dx when theta is 0. So we can either know that formula, have that formula memorized from the previous, or we could go through and do our product rule. This is where it's going to be completely up to you. So I would encourage you, as soon as I'm dealing with polars, I would write x equals r cosine theta and y equals r sine theta. I would write that out, and that way you just have it sitting there in your face. So in this particular problem, x is, I'm going to replace r with what r is. So it's 1 plus 2 sine theta, cosine theta. And then on bottom, again, I'm going to replace r with what r is. So 1 plus 2 sine theta, sine theta. And now we can either find dy d theta, like do product rule, and then dx d theta. Maybe I'll do that. I think that might be the route more of you take. So I'm going to do that. So dy d theta. I have to do product rule with this right here. And so it's not bad. It's just tedious. Like, all you have to know is how to find the derivative of sine. So it's going to be first. So 1 plus 2 sine theta. Derivative of the second, plus second times the derivative of the first. So the derivative of 1 plus 2 sine theta is 2 cosine theta. So that's going to be on top of our fraction. And then we do the same thing with dx d theta. So first, derivative of the second, so negative sine. Plus the second times the derivative of the first, which is, again, 2 cosine. I'll give you a minute to get there. So dy dx in general is just dy d theta over dx d theta. So I'm just going to write this again. And then I just plug 0 in for all those thetas. Now, they're not trying to kill you on time. Obviously, you guys are limited time on your AP test. So if it's a multiple choice question, I've noticed a lot of times they'll leave the choice. Like they might say find dy dx, and the choice might just look like this, and you just have to find that answer. Like they might leave it messy, and you just have to make sure you're paying attention to the correct signs. Or they might, like if they said find it at like theta is pi over 3 or something, they might not have you do all that unit circle evaluation, and they might leave it gross looking with just a bunch of pi's over 3s within those trig functions. So to save you time of having to find, because it'd take a long time to find all these values. With 0, it's not so bad. All right, so let's plug 0 in for theta. Let's see. Sine of 0 is 0. So that's going to be 1 times cosine 0 is 1. Plus 0. That's nice. And then on bottom, 0, 2. So 1/2. So that turned out rather nicely. Sometimes they'll say find the equation of the tangent line. Well, if they do that, then you have to find x and y. So if they would say, you're doing like point slope form, but if they said find the equation of the tangent line, you would have to use your xy definitions here to find your x and y coordinates at 0, just as your xy values, and then do point slope form. So that can happen. So sometimes you use these definitions, the r cosine theta, r sine theta, to find x, like what x and y actually are. Sometimes you use them to find the derivatives. They're probably the most used formulas with your polars. You guys want to try A? You want to try it? Try it. Try 2A. These are the last 3 examples we're doing today. Try 2A. I triple dog there, yeah. Sarah, you dive in.
I did. Thursday, I think.
Yeah.
It's fine. I didn't have, like, you have to have a full 6 do for luxury, and only 2 people can do for luxury. So I only did like 3, but then.
They all hold like 10s in my school.
Not quite.
I wonder what the state record is for dive scores. Has anyone ever gotten 10s? But did he get 10s? Did he? I know he went here, but did he dive in high school, like state championships? He did.
He's on the record board.
We've had some really good divers, girl divers too. Had some state champions. I think your homework tonight's only 3 problems. So, I mean, once you know how to kind of do this, it's fine. So I know some of you aren't all the way done, but my hope is that you can at least get to what dy dx is. If you can get to what dy dx is, then you're in good shape for whatever they're going to throw at you. Just take your time with the unit circle. I remember if this is a free response question, which it could be, I would 100% stop at this line right here. In fact, you don't even need to get to this line. Now that I think about it, if you want, find your derivative, you could put pi over 6 in for all these thetas, and you could stop there on a free response question. You don't have to evaluate any of the trig functions on a free response. So just keep that in mind. And I highly doubt that this is going to be a multiple choice question where they're going to have you get all the way down to the end. This work is nasty. But if you do get all the way down to the end, it turns out to be -1, which is pretty nice. But they're not going to have you do that. They just won't. They're trying to test calculus instead of testing all this manipulation inside of here. So I wouldn't worry too much about that. I would make sure you know how to find dy dx and know how to use the unit circle. But aside from that, I wouldn't stress. What do you guys think before we do the next 2? Okay. Okay. The last thing they could ask with derivatives is this. They could say, find the point at which the tangent line is vertical and find the point at which the tangent line is horizontal. Again, like parametrics. We did these with parametrics. So going back to, I should write this up here. I don't need to rewrite it. I'm going to be lazy and just show it here again. So if I want to figure out where the tangent line is vertical, then that's where dx d theta, the bottom of this, is going to equal 0. So if they're asking for vertical tangent lines, set your denominator of your derivative equal to 0. Horizontal tangent lines, set your numerator equal to 0. So we are going to have some trig functions to solve. This is right up Mr. Porter's alley. We're going to have some trig functions to solve. So for the ones that are vertical, we're going to set dx d theta equal to 0. We're going to solve that. So going back to the derivative, it was -2 sine theta cosine theta. We're going to see what you guys remember. All right, so I just set the denominator of that derivative equal to 0. Who remembers how to solve trig equations? Emery, do you remember how to solve this? No? Anybody remember? What do you think, Alex?
Well, the first thing I would do is divide both sides by -2 to get rid of that. Then I would.
That works. I'll stop you there for a second. So you're saying divide everything by -2?
Yeah.
Okay, I like that idea. Not necessary, but it definitely cleans things up. Okay.
From there, I would move. I would subtract sine theta, cosine theta from one side, move it from the other, and then proceed to divide by it on both sides. If that makes any sense.
Well, make sure you're not dividing by variables ever, because you're going to lose solutions that way. I would encourage you, at least this is the biggest advice I can give. When you guys are solving trig equations, you want it to equal 0. I would keep everything on one side of the equal sign. What you're doing at this point, you're either looking to factor, or what happens, I'll show you what happens on the next one. So I'm going to leave it in suspense there. So if I'm looking at this, I'm not going to distribute the sign inside of here. I guess you could. But I can't multiply sine theta, cosine theta together. And like I said, I guess I could distribute the sign. But when I'm solving these, the first thing I look for is, can I factor stuff out? And I notice between these two terms, they both have sine theta. So I'm going to factor sine theta out of each one of these. And if I factor out sine theta, well, from the first one, I'm left with cosine theta. And the second one, the sine's gone, so I'm left with 1 plus cosine theta. Then I'm going to combine like terms. But the reason that we want it to equal 0 is because once you factor, then you can set each factor equal to 0 and solve each one of those little trig equations. So now I'm after, okay, I'm going to set sine theta equal to 0. This is kind of the fun part. I don't know why. This is always enjoyable to me. And then set 1 plus 2 cosine theta equal to 0. And I'm going to solve each one of these. So now I got to think about the unit circle. We are defined on the interval 0 to 2 pi. You told us that at the beginning of the problem. So what's this going to be? Where's sine of theta equals 0? 0 and pi on the interval. So theta equals 0 and pi. I'm going to list these out over here. So I get 0 and pi from that one. And then the second one, subtract 1, divide by 2. So now I'm after, where does cosine theta equal negative 1/2? And I will just tell you that it's 2 pi over 3 and 4 pi over 3. So for what we know right now, these are the theta values where the function has a vertical tangent line. There is one thing to keep in mind, and I have never seen it show up on the AP test, but right down here at the bottom, it says if both dy d theta and dx d theta are 0 at the same theta value, you can't conclude anything about that theta value. So if they just said vertical, you would technically also have to find, even if they didn't ask about where is the horizontal, you would technically have to find where the horizontal ones are. I've never seen this show up, but it could. So now we got to find where the tangent line is horizontal, and if we get any matching theta values, we just discard those. We can't draw any conclusions from those. So for part C, the very last one, we're going to set the numerator equal to 0. Are we having fun yet?
Absolutely.
Nice. Nice. All right. So we're going to set the numerator equal to 0. So I mentioned on the first one, if you could factor stuff out, factor it out, and then set your factors equal to 0. Well, on this one, there's nothing to factor out. The first term has sines in it. The second one has cosines in it. So here's the second way you solve trig equations, is actually multiply your stuff out. So we're going to start there. So this would be negative 2 sine squared theta. And then for the second one, I'm going to distribute the cosine. But remember what the next trick is? Yeah. So when you're dealing with quadratic trig equations, you want to get either all cosines or all sines. You want to get one or the other. Since there's a linear cosine function here, that means I want to keep the cosines. There's no way I can deal or combat this cosine. So I want to change sine squared theta to be in terms of cosines. So this is the Pythagorean identity. Sine squared plus cosine squared equals 1. So sine squared is 1 minus cosine squared. So I'm going to change this to be 1 minus cosine squared instead. And then we basically have a quadratic equation on our hands. So distribute. I'll wait. Then I'm just going to write it like in order of a quadratic. I got my quadratic term, my linear term, my constant. Alex, I like your idea about just dividing. So you can't divide by variables. You can't divide by thetas. You can't divide by x's in math. You can only divide by numbers. So I'm going to divide everything by 2 just to make this a little easier on ourselves. And then we just have to factor this. So I know it's going to be 2 cosine theta, and the other one's going to be cosine theta. The only options for the constants are 1 and -1. It's just a matter of which goes where. So we got to get positive cosine. So it's got to be -1 + 1. Because if I did my inner and outer terms, I would get +1 cosine theta. Woo! And then just set each factor equal to 0. So for cosine theta equaling 1/2, we would get theta equals pi/3 and 5 pi/3. And the other one would be pi. So since pi showed up for the horizontal and vertical, we can't draw any conclusions. We're going to discard. I don't know how you would find out if it is. I'm rereading that note there. It says if they're both 0, no conclusion can be drawn about tangent lines. Does that mean it could be vertical or horizontal? I don't know how you would determine. These are just my inner thoughts. I don't know. But for now, we're going to exclude it from both. Did any others show up? No. There we go. This is the easier of the two, I think. And hopefully I'm not stepping out of bounds when I say this. I don't think there's anything in particular in this lesson that's extremely difficult. It's a lot, but there shouldn't be anything in here where we can't do. Mainly comes down to taking your time. You guys got any questions at home? Am I muted? Are you guys muted? Are you frozen? Let it go. Let it go.
We're big chilling. That's what we're doing.
What's that?
We're big chilling.
You're chilling? Like a villain?
Yes, sir.
Word. All right. So before next time, your homework tonight, like I said, is 3 problems. I don't know how long it will take, but I would encourage you to watch those videos. And it's kind of just you learning the material ahead of time and then learning the lesson. The first year I taught this class a couple of years ago, I encouraged them to kind of see what the next lesson was going to be and just try to learn it a little bit ahead of time. That way, when you come into the lesson, like you at least have somewhat of background knowledge. I had one girl who did it. None of the rest did, but she said it really helped. She said she started trying to learn the stuff before coming in, and then hearing me teach it like made everything make a whole lot of sense. So anyway, all right, you guys are free to go at home. I will see you Thursday.